Hey everybody, welcome back. This is Introduction to Statistics at College of the Sequoias, Math 21 at our school. In today's lesson, we're covering Chapter 6 in its entirety. And Chapter 6 is on discrete probability distributions. And I'm going to give you a summary right off the bat, so that if you're watching this video later, the first couple minutes have everything you need as a quick summary. So 6.1 is on discrete random variables. And the basic probability model and probability distributions. And what you need to know from there, in summary, is the expected value. We're going to take the sum of x, our values, times the probability of x. And I'm going to lecture on this. And if we have a table, if it's in tabular form, in Statcrunch, SC is Statcrunch. In this section, we will use stats calculators custom. Okay. Then we get to 6.2. 6.2 is on the binomial distribution. Binomial probability distribution, to be specific, but often we just say binomial distribution. Important takeaways from this. First off, the mean is n, the number in the sample, times p, the probability. So the mean of the random variable is n times p. And the standard deviation of the random variable is the square root of n times p times 1 minus p. Other things you need to know, the scenarios, it's a very specific scenario, and we have requirements. So 1, there needs to be a fixed number of trials. 2, the trials are independent. 3, there are 2 mutually exclusive outcomes. 4, the probability has to be fixed between each experiment. Probability has to be fixed for any given outcome. For each outcome, there's 2 of them. But not necessarily 0.5 each. Okay. And in Statcrunch, what we'll do there is stats, calculators, binomial, pause this for a second, and there's one more section in chapter 6, and then we'll just dive into the meat of this. So 6.1 is on probability distributions in general. 6.2 is on the specific one, the binomial probability distribution. And finally, 6.3, our final one for this section, is another specific distribution. It's called the Poisson probability distribution. And what we need to know from here, again, it has a mean and a standard deviation for the problem for the random variable. So the mean is lambda times t, where this is the rate. And that's t is often time, but not necessarily. You'll see when we dive into it. And so it's just simple multiplication, and just like on the binomial, or very similar to the binomial, when we find the standard deviation, we're taking the square root of that, but we don't even need to modify this by adding anything else. It's just going to be the square root of the mean. Okay. This also has criteria that must be met, but most often you'll be informed that a scenario follows a Poisson distribution. It looks like the word poison, but there's an extra S. If it doesn't tell you, we'll go into that later in that actual section. What you need for this section to remember is the Statcrunch commands are stats, calculators, Poisson. All right. All right, so let's dive into it. So to start this off, we need to start discussing what a random variable is. So a random variable is a numerical, random variables are numerical measures of the outcome from a probability experiment. Okay. We often, quite frequently, use X. So capital X describes the category of outcomes that's hard to read. Let's put it down below. It describes the category of outcomes. And lowercase x is a list of all the possible numerical outcomes. All right. What does that mean? Let's just give you an example. What do I mean by this? So let's say Vivian and I try to decide an outcome playing rock, paper, scissors. I'm assuming that, and this is an assumption, everybody has played this game. This doesn't take any props. Your hands. If you don't have hands, it's a little different. But we're trying to decide an outcome playing rock, paper, scissors. And so we're going to play 5 times. And what I'm going to use to make this a numerical, I need my random variable numerical. X will be the number of times I win. That's my capital X. And lowercase x will be the possible outcomes. So, what could x be? Well, I could win 0 games, and Vivian could crush me, just kick my ass left and right. I could win 1 time, I could win 2 times, I could win 3 times, I could win 4 times, or I could win all 5 games, okay? And the way we use the turn this into a probability model is we say, what is the probability that the number of times I win equals a specific value? What is the probability that the number of times I win or what the number of times I win is the same thing as the random variable. And in the future, I'm going to use RV for random variable. Writing out random variable repeatedly in this chapter is going to suck. So I'm going to use RV. What is the probability of the number of times I win, which is the random variable, equals a specific amount, or a specific value. And that's my numerical outcome. Now, that's just this scenario. In other scenarios, capital X is going to equal something different, and lowercase x is likely to have different values. And what makes this a discrete probability model? This is a discrete model because x takes on countable values, on a limited number of countable values. One, two, three, four, ... In this case, 0 also. if we could go up to 100, we could go up to 1,000. It could be 10 billion, but it just has to stop. Okay. Like we could do a probability distribution on the number of leaves that fall off of an oak tree in October. That could be a lot, right? If the wind's really strong, well, let's even go November. Somewhere in October, November, fall, where the leaves are starting to fall. God, I hope oaks lose their leaves. I think they do. I'm not a plant expert, not a botanist here. It could be very windy. They could lose a lot of leaves. They could lose all their leaves. It could be hundreds of leaves. Or maybe calm air and the tree is strong and it doesn't lose any leaves. So it could be a large number of leaves. It doesn't have to be small. Okay. So the number of outcomes is countable. That makes it a discrete random variable. And if there's infinite outcomes, or continuous, like or comes from measuring, like time, distance, stuff like that. We call this a continuous random variable. And we'll look at that in chapter 7. And I'll just write down some examples. Length, weight, time, things we measure. Now I said the probability that our category, our random variable x equals a specific value, lowercase x. But we're not limited to the equal sign. We can also use our inequality symbols. We could have less than or equal to, greater than or equal to. When you hear the words, I'm going to add this in because students were asking me about it. If you hear the words inclusive, the symbol is going to be one of either the less than or equals to or the greater than or equal to, depending on the scenario. Likely the less than or equal to one. Because it means it's including the value that it equals to. It's including the equal portion. That's what inclusive implies. So that's what we mean with random variable. Let's look at probability distributions. The scenario I just described here, well, we can actually look at it in 6.2. This is a binomial distribution. I was mentioning it to you earlier. There are a fixed number of outcomes. There's up to 5 games. There's 5 games. The probability is actually equal in each game. It's fixed. If no matter what one I throw, rock, paper, or scissors, there is one value that beats it, and there's one value that it beats. So it's 50-50, 0.5 for each. And it meets the requirements of the binomial. We'll come back to that. But not all probability distributions meet that. So let's just look at probability distributions in general. And this is frequently shown as a table listing all possible outcomes and their probability. And let's just use a different example. In fact, it's probably not a very good example right now. I am filming this during the COVID pandemic. So you'll see why this doesn't seem like a good scenario. Example is the number of movies streamed on Netflix in a month. And it does fit the scenario. A lot of people are watching Netflix right now. The values I have, though, are probably way off. So the following values are probably not correct right now. In fact, I know they're not going to be correct. During a lockdown pandemic. Hopefully this is the only one we have in a really long time, but could be others. So let's just, so our table, I said we have a table, let's draw a table. So what I'm gonna do is the number of movies streamed in a month, that is my random variable. So that is my random variable. Number of streamed movies. My possible outcomes in this scenario, we're going to keep it small. I'm about to write possible incomes. That does not make any sense in this. Possible outcomes. Let's just say it's 0 through 5. You may not watch any movies on Netflix. Definitely the case if you don't have Netflix. But you might watch 1, 2, 3, 4, 5. I'm imagining right now it might be a lot higher. So let's do our probability table distribution. I will make a column for the values. I'll call those values the lowercase x. And the other column I'm going to use is P of x, the probability that they happen. And so the way you read this table is, this is like the probability that big X, the number of streamed movies, equals 0. And I'm going to say it's kind of low, 0.06. And in each of these cases, big X equals a specific value. So probability that X equals 1, X equals 2, probability that X equals 3, probability that X equals 4, and probability that X equals 5. That's what this means. And let's give it some values. So 0 movies will be 0.06. 1 movie will be 0.58. 2 movies will be 0.22. 3 movies will be 0.10. And it starts to taper off, get lower. We're going downwards. 4 movies, 0.03 or 3%. And 5 movies, 0.01 or 1%. And the way you read it, this thing over here, probability that number of movies equals the number. X. All right. So this is a probability distribution. Well, is it? Is this a probability model? we've discussed some requirements for probability before. Each probability has to be between 0 and 1. That's one requirement. No negative values, no values greater than 1. And the second requirement is that the sum of probabilities, this means sum, sigma is sum, the sum of the probabilities has to equal 1. Well, these values all are less than 1 and greater than 0. So part A is met. Part B, let's add them up. 8 plus 2 is 10, plus 6 is 16, plus 3 is 19, plus 1 is 20. I'll put a 0, carry a 2. 2 plus 5 is 7, plus 2 is 9, plus 1 is 10. Put a 0, carry the 1, and the left column has all zeros except for that 1 I carried, 1. So, and this is the sum of them. I just added those up. It does equal 1, so that requirement is met. This is a probability model. Okay? Now, there's a chance you might get the data presented to you as a probability histogram. We could look at that real quick. We know the outcomes are 0, 1, 2, 3, 4, 5. And the largest probability is 0.58, so maybe let's make this go up to 0.6. 0.3 is halfway. And 0.06 is less than 1, it's about halfway. And 0.58 is all the way up near 0.6. Then I've got 0.22. .10 is right here. And then it starts to taper off really fast. It gets really low. So it could come as something like that. Question for you. What type of distribution is this? We've talked about these before. Is this a bell-shaped distribution? Is it a uniform distribution? Is it skewed left or is it skewed right? In this scenario, the hump is around the 1 and the tail to the right is longer to the right. This is a skewed right distribution. We've got a midterm coming up pretty soon. Got to start talking about some of these things, refreshing your memory. And what we have going along the left over here is the probability that x equals a specific value. And on the bottom, we have the random variables for the individual x's. Okay. And I'm going to take a second to add that into Statcrunch right here. I'm going to call the first column x. I'm going to call the second column p of x, just so that I know what I'm looking for later. 0, 1, 2, 3, 4, 5. And I'll give it values because we're going to use them in a second. 0.06, 0.58, 0.22, 0.1, 0.03, and 0.01. So I got my values in Statcrunch right there. And As a reminder, we can look at the distribution right there as a histogram, graph histogram. We want to graph P of X. Oh, that's not doing well. This is where, yeah, each of those numbers only shows up once. I can't really do the histogram in this. You have to do it by hand. All right, so what else do we do with this? We can look at the mean of a discrete random variable. The mean of a discrete random variable. If you have the actual data, of responses, like if I have recorded down, if I surveyed 500 people asking how many movies they watched on Netflix, I could calculate the mean fairly easy. I just add them all up. I could compute the mean doing add them up and divide. Compute the mean using that's our X bar formula. Add them all up and divide. When we have summarized data like we do here, we have to use something else. So what we do, we call this mean. Remember, mean is mu. And since we're doing it of a discrete random variable, we're going to say the mean of X, the mean of the discrete random variable. For a model like this, as I alluded to in the first couple minutes, the mean is, well, I told you we needed X times P of X. And we're going to take the sum of that. Take the sum of X times P of X. And this is doable by hand. This is called the theoretical mean. And let's go back to our Netflix problem and take a look at doing this by hand. Okay. So I had X, I had P of X, 0, 1, 2, 3, 4, and 5. This was 0.06, 0.58, 0.22, 0.10, 0.03, and 0.01. That's the table we had before. Now what I'm going to do is I'm going to multiply X times P of X. What I'm doing is just multiplying across, left to right. 0 times 0.06 is 0. 1 times 0.58 is 0.58. 2 times 0.22 is 0.44. 3 times 0.1, or 3 times 10 cents, is 30 cents, 0.30. If I look at this probability like money right now, which I can do easily because it's 2 decimal places, 0.03 is 3 pennies. If I do that 4 times, I have 12 pennies, or 0.112. and 5 pennies makes a nickel, 0.05 for the final one. So that's each value of x times p of x. When I add them up, I can find the sum of x times p of x. Eight plus 4 is 12, plus 2 is 14, plus 5 is 19. Carry a 1. 1 and 5 is 6, plus 4 is 10, plus 3 is 13, plus 1 is 14, and I'll carry a 1. And there's no value in the left column, so except for the 1 I carried, 1. So the mean of this is 1.49. What does that mean here for our sample? The average number of movies watched was 1.49. Now, if we had the actual data, on the Netflix subscribers, try that again. And we computed a sample mean x bar. Then this is what should happen. As n increases, the number in our sample, x bar should get really close to the mu of x we calculated. And how can I put that in terms of math? If two values are really close, the difference between the two values is close to 0. Is approximately 0. That means approximately. I don't know if I've used that in this class. An equal sign that looks wavy is approximately. And so the difference means subtraction. So x bar minus mu of x should get close to 0. Now, when I start off this discussion, I called this expected value. And this is why. Okay. The mean of a random variable mu of x represents what we expect to happen in the long run. If we have it, as n gets really, really big, there's a sample size approaches the population size. And Netflix is one of the biggest companies in the world based on number of subscribers worldwide. I think I was looking at data on it. They had like 80, it can't be 80 billion, but it's, I want to say it said 80 billion. That seems really large. It's large. It's bigger than Amazon Prime. It's bigger than other ones. Netflix has been around. So it's the mean of the random variable, mu of x, represents what we expect to happen in the long runs. Since it's what we expect to happen, we call it the expected value. What value can we expect for each outcome in the long run? All right. So let's just go over a scenario for you from the casino. Let's talk about roulette. The expected winnings from playing roulette. Playing a single number on roulette. So maybe I can pull up a table, image here. Oh, misspelled it. I had my Zoom window blocking my spelling, and I didn't see that. I mistyped it. Let's look at images. Oh, other one's better. That's better. Not really. It didn't show it. So in roulette, there's this little spinner thing. They spin the ball. There are 38 numbers. We've got 0, 00, and then 1 through 36. 0 and 0 are both 0 and 00 are green. This one actually just shows a single 0. It's not a good one. This is, if you have a chance, if you play roulette in a casino and you have a table that has 0 versus one that has 0 and 00, this has better odds for you. I don't want to use that one because it's not really descriptive of what we're doing here. Let's find one that does. Really? Just an online casino? You can't show me the darn image? This one sucks too. I should add this one already loaded. A lot of these are just showing 0 and 00, or just single 0. That there we, please load. There we go. Okay. So 0 and double 0 show up as green on the roulette wheel. And then half of 1 through 36 is red. And half of them are black. And they're not just, notice if you look at the table, they're not just the odd numbers are red and the even numbers are black. I believe, I don't know, let's count it up. How many odd ones are there that are red? I see 5, 6, 7, 8, 9, 10 odd red, and 8 even red. So they're not broken up that way. Odd and even don't line up well for red and black, but also half of them are odd and half are even. And you have a variety of things you can bet on. You can bet on things where they spin the ball one way, the table rotates the other way. Eventually the ball lands in a little bucket next to the number. Like here, the yellow ball landed on 30. And if you bet on that number or it's in the category that you bet on, you win. So the yellow 30, if you bet on the third 12, you're betting on 25 through 36. 30 is in that category, you would win. If you bet on multiples of 3, 3, 6, 9, 12, 15, 30 is a multiple of 3, you win. If you bet on red, 30 is red, you win. If you bet on even, 30 is even, you win. You can also bet on exact numbers. The values for each of these is there's 38 outcomes, and the odds of it landing in any specific outcome are 1 out of 38. And the way they do the betting on this for a single number, 38 numbers, when you bet on a single number, they pay 35 to 1. $35 to 1. And what this means is I bet $1. If I hit my number, they pay me $35. If I miss, like the ball lands on a different number than what I bet, I lose the $1. They pay me 35 bucks and I keep my buck, okay? So let's just say I bet on 13. Let me leave that up where we can see it. I like the number 13. Let's say I bet on the number 13. What are the outcomes? The outcomes, the ball lands on 13. The ball doesn't land on 13. Those are my two outcomes. Random variables are associated with something numerical. So let's make my random variable. The random variable is the amount of money won. And we're going to do this from the player perspective. Completely backwards if it's the casino. So 35 to 1. So my outcome, my random variable is my winnings. And if the ball lands on 13, I hit my number, I win a positive $35. Ball doesn't land on 13, I lose the dollar I bet. All right. What is the probability of each of these categories? What is the probability that I win $35? What is the probability that X equals $35? Well, there's only one number that works. I bet on 13, there's 38 numbers. This is one number out of 38 numbers. This is approximately, to 4 decimal places, 0.0263. 1 divided by 38. I'm going to 4 decimal places because that just seems like a good spot to stop. I don't want to go too little. Like I can't go to 1 decimal places because then it just says 0.0. Going a few out looks good. The odds that or probability that I miss, there are 37 other outcomes that the ball could land in out of the 38. 37 divided by 38 is approximately 0.973 and 6, 8. 8 says round up the 6 to a 7. You will notice if I add these probabilities up, 0.0263 plus 0.9737 add up to 1. This is a probability model. I'm going to make a table for X times P of X, or a column for X times P of X. 35, and since we're talking about money, I'm going to take it to 2 decimal places. So I had 1 divided by 38. I'm going to multiply that by 35. And to 2 decimal places, I get 0.92. And 37 divided by 38, if I just multiply by a -1, all I'm doing is changing the sign. This is negative 0.97 to 2 decimal places. The mean of the random variable is the sum. 0.92 plus negative 0.97 is negative 0.05. That's my mean. This is the expected value. And we often use capital E of X. Capital E parentheses X. Expected value of X is negative 0.05. So what does that mean? In the long run, I can expect that for every dollar I bet, I will lose 5 cents. Because this was in money. $35, $1, this is money. I will lose $0.05 or 5 cents. Note this is a long run scenario. I could bet $1, I could hit right away. And then I'm up $35. That's expected value is what's going to happen if I just play thousands of games. Eventually, the number of times I win is going to be a lot less than the number of times I lose. Even though I win a lot of money when I win, I'm going to lose more often than I win by a lot. And so the average is I can expect to lose a nickel every time I play. What does that mean in the big picture? If I play 1,000 games, Now let's go 10,000. If I play 10,000 games, how much can I expect to have lost? No, this was in terms of winning. How much can I expect to have won? To do that, you take n and you multiply it by e of x. 10,000 times negative 0.05. Negative 0.05 times 10,000 is negative $500. If I play 10,000 games, I can expect it, and do just $1 a game, I can expect to be down $500 at the end of the show. Now, this is an interesting thing. If you look up roulette, the fun fact about roulette the expected value is always the same, no matter how you bet. No matter how you bet. The way they do the payouts, if you bet on odd, you bet on even, you bet on red, you bet on black, you bet on the first 18, you bet on the second 18, it's all 2-to-1, or a 1-to-1. If you bet on one of the rows where it's 12 numbers like that, it's 2-to-1. The expected value, no matter how you bet, $1 bet, the expected value is always negative 5 cents. The house earns a nickel. The house, which is the name for the casino, the house earns a nickel for every dollar bet in the long run. If they didn't expect to win money in the long run, casinos would not do it. It's not good business. I kind of wanted to call bullshit on that, but if you actually work it out, do this expected value table, given the odds, the payouts for each thing, you will find it to be true. This actually is a good site. It shows it. It even talks about it. The probability is 1 out of 38, and it goes through and shows them. Oh, look, it even shows expected W is winnings. They use W instead of X. Expected winnings at negative 0.05 or 5 cents. And they took it to even a few more decimal places. So if I did 10,000, it would actually be $526, not $500. And notice, look, they do the straight bet is one betting on a single number, betting on 2 numbers. The expected winnings is negative 0.0526. If you bet on 3 numbers, the expected winning is again negative 0.0526. And you can go down this entire list. The expected winnings is always negative 0.0526. It's the way it's set up. All right. Let's give you another example. Let's say a term life insurance policy. So let's say a lady pays $530 annually for her life insurance. For her life insurance policy, and the policy pays out $250,000 in case of death. That's so her family can pay for the funeral and have a little something extra. And this is for a specific age range. Life insurance policies are different for different categories of people. And let the probability of survival for a lady in her age bracket with her conditions. Survival for a lady in her age bracket, for a lady of her age, is 0.99791, highly likely to live. What we're going to do is compute the expected earnings for the company. It should be positive, right? It's a business. It's a business, so it should be a positive value. So we need, our random variable needs to be numerical. Let's make the random variable x equal the amount of earnings. That's what we're computing, the expected earnings. So we'll make our random variable earnings. And there's only two outcomes that the life insurance cares about. She lives or she dies. So let's make a table based on that. Okay. Pause it if you need to finish writing this down. We're going to use those numbers in a second. All right. So, outcomes. And then we look at x, and then we'll do p of x, and then we'll do x times p of x. And we know there's two outcomes. She can die or she lives. If she dies, they have to pay out $250,000. Death. They pay out $250,000, but they've already collected. They already collected the annual value insurance, which was $530. So they earned $530, but they lost $250,000, and that's $249,470. That's a loss. If she lives, they pay out nothing. No payout, they keep the $530. All right. Now, the probability of living they gave us, this was 0.99791. How can I figure out the probability that she dies? So we know probability if she lives is 0.99791. The other outcome is the probability she dies. What does that equal? We don't know. We do know those are the only two outcomes, so these have to add up. Probability of living plus the probability of dying has to equal 1. So 0.99791 plus what equals 1? I'm just using a question mark for my variable here because I've used x up there. I don't want to confuse you. I can just subtract 0.99791 from both sides. My equal sign comes down. My question mark is 1 minus 0.99791. And that the e to the negative -3 means move the decimal left 3 times. 0.00209. Okay. I guess I need that calculator because now I've got my table. These add up to 1. You can verify it by adding them. Now I just got to do the values. I'm going to do 249,470 times 0.00209 equals, and this should be negative. And I'm going to go to 2 decimal places because we're talking about money. Negative $521.39. And if she lives, they get 530 times 0.99791. Should be close to 530. 528.89. Before I go on, I want to put this in other words. Remember when we have 2 outcomes, we can do the subtraction thing. So probability of dying has to equal 1 minus the probability of living. Remember our complement outcomes, probability? We talked about this in chapter 5. And that's how I came up with that. So what's the expected value? Well, when she lives, they earn $528.89 in the long run. And if she dies, they lose $521.39. You add that up, it's only $7.50. Not a lot, is it? They can expect for a life insurance policy in the long run, each policy in the long run only pays $7.50 per year. For this category of people, her age, only pays $7.50. That's not a lot, is it? That's per customer for 1 year. Per customer per year. What if they sell 1 million policies? $1 million policies, and each one gets $7.50. That's 7.5 million. For $7,500,000. Now that's looking like a pretty good deal. It only works if they have a lot of customers. They need a lot of people. Otherwise, if they only do it for 2 or 3, they might only make, if they only have 3 customers, at most they can earn, $1,500 a year. Or if they lose, they could potentially have to pay out all 3 and pay out $750,000. This only works when they have a lot of customers. That's why the policies are made that way. Okay? So I discussed how to do it by hand. Let's show you the Statcrunch way. The Statcrunch way, and I did mention it in the beginning. I'm going to do stats, calculators, custom. What we use here, I told you that. Let's go back to our Netflix one, and we'll work from that one. Then we'll add in this one with the term life, show you it. So I'm going to go stats, calculators, and then custom is, Windows in the way. Stats, calculators, custom is down here. Notice that they are alphabetical on the calculators list except for custom. Custom's at the bottom. And even though there is a lot of them on this list, we're pretty much going to use binomial, we're going to use normal, we're going to use Poisson, and we're going to use custom. We really don't use a lot of the rest in this class. So I'm going to go custom. What does it prompt me for? It asks me for values. What are my choices? If I do select variable, it says X and P of X. Those are my column names. So it asks for columns. The values column, what you want to choose there is your X or your outcomes. And the box that says weights, the weights in column, that should be your P of X. And recall when we did this, this was 1.49. It gives you some options. Look at this. It's saying probability that X is less than or equal to 1. Notice that this actually looks like that histogram we drew, didn't it? If these weren't just narrow columns. When you're doing it, if you can see the screen, it's red for the columns it's selecting. The probability that X is less, it gives me the mean first off, the 1.49, that's what we discussed. It actually gives us our standard deviation. And you can look at doing the probability for any given range. So this one says X is less than or equal to 1. It's adding up the 0 and 1 column. You have options that you can change the symbol there. I could say just equals 0.58. In fact, that's directly from the table. We could say the probability, we can change it to X is greater than 0. That's going to include X greater than 0 includes X equals 1, X equals 2, X equals 3, X equals 4, X equals 5. It just doesn't include the 0. The 0 on the screen is black. The other columns are red. It's adding up the red columns. So it'll show you what it's adding up. Okay. Also on this screen, so let me write that down. It shows the mean and standard deviation. And you can customize categories or customize what you're looking for. Do you want to know if the probability that x is greater than 1? Do you want to know that the probability is x is less than or equal to 3? We could do that. Less than or equal to 3 is that symbol. We change that to say 3. Click compute. Less than or equal to 3 means 0, 1, 2, and equals 3 includes the 3. Those 4 columns are in red. It is adding up 0.06, 0.58, 0.22, 0.1, and it gets 0.96. So you can do things like that. You can also do range or regions. I could also do something like probability that 1 is less than or equal to x, less than or equal to 4, by clicking on between. Okay. And note, Statcrunch shows this. When you click on between, it shows this. Probability, it's got a box for entering. It says less than or equal to x, less than or equal to box. And then it has the output box. That's my output, tells me what the result is. Since I want 1 is less than or equal to x, less than or equal to 4, for this one, I'm going to put a 1 here, and I'm going to put a 4 here. What if I want probability that 1 is less than x, less than 4? If I put the 1 in, it's including it. This doesn't include 1 or 4. Which means it includes 2 and 3. So what I have to enter there, I can't use the 1 and 4 when it's that symbol, because that is not an option in Statcrunch. I can't change the symbols there. So sometimes you have to think a little bit. I can't use 1 and 4 because I don't want 1 and 4. I'm not including those values. So I have to go to the next value inward. The next value inward is 2 on the left and 3 on the right. So, and I'll illustrate both. The one that I said 1 is less than or equal to x, less than or equal to 4. Notice 1, 2, 3, 4, those columns are in red. It's counting up each of those. The probability. Okay. If I want 1 is less than or equal to x, less than or equal to 4, I only want the 2 and the 3. I'm not including 1 and 4, which means I just need to change this to 2 and 3. If I do that, notice the 2 and 3 are the ones in red, and 1 and 4 are not. That works. Or I could even do something like this. If I just change 1 to 1.001 and 4, I lower it down to 3.99. That's between it. That's not including 1. That's not including 4. I think it's easier to just go down to the next whole number, though. Go to the 2 and the 3. Okay? So that's it for 6.1. Pause this real quick. We'll do 6.2 and 6.3. All right, so that was 6.1. Let's take a look at 6.2. 6.2 is on binomial distributions. now that we've covered some of the other ones, binomial and Poisson go a little bit faster. So the hardest part of the binomial distribution is recognizing that a distribution is binomial. Working with a binomial distribution, is recognizing that it meets a binomial distribution, that a distribution is binomial. And the reason why is the 4 requirements we have. There has to be a fixed number of trials. We have to state in the beginning how many trials we're doing. You can't just go like, it can't be like baseball, the World Series is the first team to win 4 games. That's not, the World Series doesn't always take 7 games. Sometimes it's done in 4 games. That's not a fixed number of trials. A fixed number of trials, a trial is an experiment, so the experiment is performed a fixed number of times called trials. And those are trials. That's our first requirement. The second one is the trials must be independent. Which means one trial does not affect the outcome of another. So rolling dice works, counts. Drawing cards without replacement doesn't. Because it's not independent. If you draw it like on the drawing of cards, if I draw up the ace of spades, that affects the probability, that affects the outcome on the next one because there's only 51 cards left. B and C are, well, no. B and D are kind of related. C is there are 2 mutually exclusive outcomes. So for the dice, I could say rolling 2 dice, 2 die roll. I could say one outcome, roll a 7, and the other outcome is not roll a 7. But I can't just list each outcome 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You can only have 2 outcomes. They don't have to be equal. On cards, if I don't do it, if I have it with replacement, if I just draw a card and I put it back, I could break this into regions. I could break it up into suits. I could say draw a diamond or not draw a diamond. I could say draw a black card or not draw a black card. I could say draw a face card or not draw a face card. So you can do many of these things in that scenario. In the rock, paper, scissors game, I could either win or I could lose. Okay. And finally, D is related to B. The probability of success is fixed between outcomes. Or is fixed between trials. Fixed for each trial. Again, doesn't have to be 50%. Like rolling a 7, not rolling a 7 is not a 50% chance for each. Drawing a spade or not drawing a spade is not 50% each. Drawing the ace of spades or not drawing the ace of spades is not 50% each. Okay. So let's just run through some scenarios and see, are these binomial? Are the following scenarios binomial? Let's go back to our rock, paper, scissors with Vivian and David. So first option, rock, paper, scissors with Vivian and David, and they play 5 games. Not best of 5. They play 5 games. Vivian and David. And from my point of view, success is I win. Failure is I lose. They happen to be 50-50 each here. And our random variable was the number of times I win. That's why I made success the win. That promotes what's considered a success. So we got to go through the options. Does it meet our things? Get rid of that for a second. Is there a fixed number of trials? Yes, there was 5 games. I didn't rewrite it here. We talked about it earlier in this video. Yes, there was 5 games. Are the trials independent? Now there's some room for argument here. Some people would argue that with a good psychology background, what someone does before, you might be able to predict what they're going to do next. But let's just assume I throw out random hand signs and Vivian throws out random hand signs. And whether or not I repeat what I did before or change to a different symbol, they're not related. What I do in one toss has no connection to what I do before. Yes, they're independent. 3, are there 2 mutually exclusive outcomes or disjoint outcomes? I could win or I could lose. Yes. And finally, is the probability fixed for each trial? It doesn't matter if I play rock, paper, or scissors. In each of those, one of the hands Vivian plays. Let's ignoring ties. Let's just say if a tie is done, we repeat the game. That's important. So ties are discarded, don't count as part of the 5. That way we have 2 mutually exclusive outcomes. Okay. So if we ignore ties, I can either beat them, or I beat Vivian, or she can beat me. Yes. So this one's a yes. Also, this scenario is binomial in nature. This leads to a binomial distribution. Let's give you a few more scenarios and have you determine if they are. So next example. I want to see how completion of homework affects grades. So I go through the grades. Until I find 10 students that are current on their homework. And compare their grades. And examine their grades. Is this binomial? Go through the list. It's got to meet all 4 requirements: a fixed number of trials, independent trials, mutually exclusive outcomes with a fixed probability. All right, I'll assume you paused and did it. A, fixed number of trials. Do I have a fixed number of trials? I go through the grades until I find 10 students that are current on their homework. No, this is actually not fixed. I might have to look at 10 students. I might have to look at 100 students. I might have to go through 500 students to get to that value. So I might need to look at more than 10 students to determine this. I might need more than 10 students to find 10 that are current on homework. So no, this is not. It does not follow a binomial distribution. And I alluded to this earlier, so this one actually doesn't help. I roll a pair of fair dice. A pair of fair dice are rolled. Turn off alarm. Yeah, I got Game of Thrones music as my alarm on my phone. A pair of fair dice are rolled 10 times. The number of times The sum equals 7 is recorded. i.e., that's my random variable. Random variable x is number of 7s rolled. Nope, sorry. Yeah, x is the number of 7s rolled. Is this binomial? So we have a fixed number of rolls at 10. That meets requirement A. Dice rolls are independent, which means the trials are independent. That meets requirement B. There are 2 outcomes that are mutually exclusive. I roll a 7 or I don't roll a 7. If I had decided to keep track of every roll and what the value was, whether if it was a 7 or not, it would not be binomial. But in this case, I'm just recording 7s versus non-7s. So that one works. And finally, D, is there a fixed probability of getting a 7? Yes, there is. The outcomes that work are 1 and 6, 2 and 5, 3 and 4. The first die could be 4, the second die could be 3. I can have 5 and 2 or 6 and 1. There are 6 outcomes out of 36 possible. The probability of rolling a 7 is 1 in 6 if I simplify. So this is binomial. So I'm going to show you the formula for a binomial distribution. And you can do this by hand, and then you're going to see that you don't want to. And that's why we'll do it in Statcrunch. So assuming a binomial probability distribution, how can we calculate the probability? The formula is the probability of getting X is N choose X. Remember our counting things in probability? N choose X, and we're going to multiply that by P raised to the X. And then we're going to do 1 minus P raised to the N minus X. Horrible formula to work with. Because there's too many chances for error, or too many opportunities for error. You might enter it in the calculator. You might have all the values right, have all the numbers right, and in the calculator wrong. But you should know what they are. N is the fixed number of trials. X is the number of successes. And P is the probability of success for a single trial. Which makes 1 minus P the probability of failure. And success, failure are arbitrary. Some scenarios, it's like, whether, if I don't care if I roll a 7 or not, and I'm just recording the outcome, is it really a success if I roll a 7 if I don't care? No. But it's a way of categorizing the two things. So success or failure. And to use Statcrunch, since this is a horrible formula to use, this is easy in Statcrunch. And when I say easy, maybe I should use capital letters easy. Easy, big easy in Statcrunch if we know N, X, and P. That's all we need. We need to know the number of trials that we're working with. We need to know the number of successes that we want. And we need to know the probability of success for any given trial. When we do it, stats, calculators, binomial. And we can take a look at it right now. I need N right there. I need P. And I need to know what X equals. Notice I have a drop-down menu for the symbols. Well, I actually mentioned the symbols earlier, but maybe I should actually go through them, talk about the inequality symbols. This has a normal tab and a between tab. So it has both, but we do need N, P, and X. So notice it uses, notice there's an option for the symbol. Notice there's options besides equal. Probably with X equals a number. We have that symbol, we have that symbol, we have that symbol, we have that symbol on the standard tab on the drop down. So maybe we should talk about what those symbols are. I mentioned them earlier, but if you're unfamiliar with them, I think maybe I should be a little bit more thorough. Those are called inequality symbols. And let's include phrases that go along with them. What words you might see that go along with them. So, if I see the words at least, no less than, greater than or equal to, these are all giving us this symbol here. X equals the number in question. So let's say X is greater than or equal to A. X equals A or any number larger than A. That's what that reads. And the symbol is like that. If you like, make it an alligator mouth, put teeth on it, vampire. Vampire, the alligator wants the bigger meal. It's going for the larger number. Okay. Another thing you can see, we could see at most no more than or less than or equal to. That one is the symbol going to the left. Or the alligator is biting to the right, the tail is to the left. And if I put the X and A in again, X equals A or any number less than A. Then we have our strict inequalities. We could have more than or greater than. Larger than, above, something like that. This value, that symbol, alligator going to the left with no line underneath it. The line underneath it indicates the adding of the equal part. So if I don't have the equal part, this says X is a number larger than A, but not A. So that line underneath means we include the A in the possible outcomes. And you can see that here in the Statcrunch calculator, the binomial calculator. I have excellent less than or equal to 5. Right now, I got the 0, 1, 2, 3, 4, and 5 in red. As soon as I change it to the less than, it gets rid of the 5. It's only counting the 4 downward. All right? Which leads to the final category, the less than. It often says things like fewer than. That's a phrase that shows up, less than. And we have that symbol. The alligator goes towards the A. X is a number less than A or smaller than A. But it can't be A. And I guess for the sake of including all the symbols, the equal sign should be in there. What words show up? And everyone knows what equality equals, but what words show up there? We might see the word exactly. Is. The rule is 7. The rule is exactly 7. The rule equals 7. And those all lead to the symbol X or equals. And that is X equals A and no other value. So let me just give you a scenario, and we'll use the calculator to show it. I'll actually show you in the formula what's going on. And then we won't do that anymore. So, example. "35% of car owners have 3 or more vehicles." Let's say cars, not vehicles. Vehicles could include other things. We sample 20 homes to see if they have 3 or more cars. So, is this a binomial experiment? I have a fixed number of houses I'm going to check. The number of trials is 20. It's fixed. Yes. Are the trials independent? Yes. Each house should be different than its neighbor. Are they mutually exclusive? Is there two outcomes and two outcomes only? They could have 3 or more cars, or they could have not 3 or more cars. So this is mutually exclusive. And finally, is the probability fixed? We have it set at 35% or 0.35. So yes, this is binomial. And what are some things we could ask? We could say something like this. What is the probability that exactly 5 homes have 3 or more cars? What I'm doing here is I'm calculating the probability that x equals 5. And in that formula, that horrid formula, let's put it back up on the screen. I've got n equals 20, x equals 5, that's what I'm going for, and the probability is 0.35, 35% as written as that, and we're going to just put it in here. N choose x is 20 choose 5, and we're going to multiply that by p to the x, 0.35 raised to the 5th power. And then we're going to do 1 minus 0.35, 1 minus p raised to the 20 minus 5 power, which is 15. Choose 5 times 0.35 raised to the 5th power. And I'm going to say equals real quick, and then times 1 minus 0.35 is 0.65 raised to the 15th power. That little caret symbol is the exponent sign, and we talked about that in math lab, I believe. Maybe not in your guys' class. The calculator is telling me 0.127199185 in the calculator. In Statcrunch, what do we get? I'm doing n equals 20. The probability of success is 0.35. And I want to know the probability that x equals exactly 5. Look at that. Just spits it right out. No chance of screwing it up on a calculator. In Statcrunch, all I enter is, well, first off, you got to remember you're going to go to Stats, Calculators, Binomial. Enter n equals 20, p equals 0.35, and set p to be x equals 5. Click compute. This one has a lot of room for error just doing the exact probability. What if it was more challenging though? What if I say, what is the probability that less than 4 homes do? have 3 or more cars. If we're doing it by hand, the probability that x is less than 4 is that symbol right there, which means that it's the probability that x equals 0 plus the probability that x equals 1 plus the probability that x equals 2 plus the probability that x equals 3, and we don't include 4. And we have to use formula on each if we do it by hand. So I would do x equals 0, x equals 1, x equals 2, x equals 3 in this formula. What that's changing is the combinatorial up front and the exponents here. There's a lot of rooms for mistake. If I do it in Statcrunch, I just change that to say less than, and I say less than 4, and click compute. Error prone by hand. Too many ways to make a mistake. In Statcrunch, n equals 20, p equals 0.35, set p to be x or less than 4, click compute. And we find the probability that x is less than 4 is 0.044376. And what MathLab, the homework asked for, it will depend on how many answers. All right. One more scenario. Same thing, same scenario though. One more test though. Let's do probability that at least one home has 3 or more cars. At least was numbers bigger than 1, but it can include 1. That's going to be the symbol x is greater than or equal to 1. And this is literally, if we do it by hand, probability of 1 plus probability 2 plus probability of 3 plus we keep going plus the probability of 19 plus the probability of 20. Oh my goodness, this would be tedious by hand. We do have the option. Remember, the sum of all probabilities has to equal 1. We could use the complement. The complement of probability x greater than or equal to 1 is the probability is x is less than 1, or the only value less than 1 is 0. Which would make it, if we did that, we could do probability that x is greater than or equal to 1 is 1 minus the complement, or 1 minus the probability x equals 0. And we could do the formula. Again, still error prone, or we can just go into Statcrunch, enter in our values, and we're going to say x is at least 1, x is greater than or equal to 1. Click compute. And notice all of the columns are red. You can't see it very well. The first column is black. It's including everything but probability that x is equal to 0. Probability that x is greater than or equal to 1. In the binomial scenario, this with 20 is n, p is 0.35, 0.9998185. And if we want to do, let's say the number of homes is between 6 and 12. So click on between in Statcrunch. And the symbol is forced to be probability of blank less than or equal to X less than or equal to blank. And the wording here is a little vague. Do we include the 6 and 12 or do we not include the 6 or 12? This is where you'll see, like in the homework, they should say use the word inclusive. Between 6 and 12 does not imply the numbers between 6 and 12 are 7, 8, 9, 10, 11. So I would need to do probability that 7 is less than or equal to X, less than or equal to 11. Okay, if it said the number of homes is between 4 and 9 inclusive, that means include the 4 and 9. Which means my options are 4, 5, 6, 7, 8, or 9. And Statcrunch will actually use the 4 and 9 there. So that, if you see the words inclusive, it means include the values that it's saying it's between. If you don't, it's the other way. And if you need to know the mean and the standard deviation, you'll need a calculator for this. They're straightforward in a calculator. Mu of X is N times P. Sigma X is N times P times 1 minus P, and we take the square root. So back to the homes problem, back to the 3 or more cars problem. N equaled 20, P equals 0.35. Mu of X, the mean of the random variable X, is 20 times 0.35. And that should be 7, I believe. Yep. And standard deviation is the square root of 20 times 0.35 times 1 minus 0.35, which is the square root of 20 times 0.35 times 0.65. And I know that part's 7. This is the square root of 7 times 0.65. Or you could do it all in your calculator all at once. I'm going to say square root. I'm going to use parentheses so it knows that I want everything underneath the square root. 20 times 0.35 times 0.65. End parentheses. Standard deviation here. 2.13307. Notice what happens if you don't use the parentheses. Square root of 20 times 0.35 times 0.65. It gives me 1.01. Entering it in the calculator, it's very specific. If you don't have a parentheses option, you'll need to calculate 20 times 0.35 times 0.65 first, figure out what that answer is, then take the square root of it. Okay? What goes on? How does this look graphically? And we can actually see it. You can see it on the binomial calculator. So let's look at some scenarios. Let's look at some scenarios. I'll do a new page for this. Let's first off say if n is low. Let's make like n 10. That's not a very big value. And let's start off with if p is 0.5 or close to 0.5. It doesn't have to be exactly 0.5. Let's go 0.49, something close. I got too many decimals right there. The graph is roughly bell-shaped. What if p is low? P is low. Let's click compute. I use 0.01, but we could try other ones. The first column is really high and then gets really small really fast. Let me go a little bit larger. It might be a little bit easier to see. Let's go with 0.1. High in the beginning, and then it tapers off to the right. If p is low, it's a skewed right distribution. And I'm sure you can guess if p is low and it's skewed right, guess what happens if p is high? Change that to 0.9. Now it's larger on the right and it tapers off as you go to the left, skewed left. We desire bell-shaped graphs. We desire bell-shaped distributions. But probability is fixed. Is fixed for binomial calculators, for binomial problems. What options do I have to get a bell-shaped distribution? To get a bell-shaped distribution, or to get a bell curve? Well, the probability is fixed, so I can't change it. And we don't really want to change what we consider a success or a failure. All we can really change is we can require more trials. We can require more or less trials. What happens if we require less trials? Let's go drop down to 5, n equals 5. That doesn't get more bell-shaped, does it? So let's go back to looking at 10. Let's go up to 20. Getting closer, maybe 30. Closer, 50. Well, it's getting bell-shaped, still more skewed left. 100. Well, now we're getting pretty close to a bell shape. The tail is a little bit longer on the left, but it's pretty much a bell shape centered around, looks like 90 around here. 1,000. Well, now we're looking like it's kind of hard to tell which side's longer. 10,000. That's a bell. If if n goes down, it's more skewed. So we need to increase n. And how do we know what to increase it to? Well, general rule of thumb. For a binomial distribution, for a fixed p, or probability, to guarantee a bell-shaped distribution, pick n such that n times p times 1 minus p is greater than or equal to 10. Okay. Let me give an example real quick. Pause this if you need it up longer. Let's say p equals 0.21. What n do I need to get bell-shaped results? How many trials should I conduct to get a bell-shaped result? I want n times p times 1 minus p to be greater than or equal to 10. I can plug in values. I don't know what n is, but p is 0.21, which makes 1 minus p 1 minus 0.21. I still want that to be less than or equal to 10. If we do that, 0.21 doesn't change. 1 minus 0.21 is 0.79. If I multiply 0.21 and 0.79, I'm going to get 0.1659 times n. It needs to be greater than or equal to 10. And I can find what n I need. I can divide both sides by 0.1659. This is a little bit of algebra. If I do, the n on the left, all we have left is n. And 10 divided by 0.1659, 60.277. And since I need to pick a value, I can't do 60.277 samples. We pick the next largest number. We need at least 61 trials. What if the probability is 0.5? N times 0.5, and 1 minus 0.5 is again 0.5. Needs to be greater than or equal to 10. Point 0.5 times 0.5 is 0.25. If we divide by 0.25, we get n is greater than or equal to 40. So we'll pick n to be 40 or larger. So you kind of want n to be bigger than 40. Some would argue 30. 30 isn't the best option. Like, let's take a look at it. If probability is 0.5 and we do n equals 40, what's the graph look like? It's bell-shaped. What about 30? It still looks fairly bell-shaped, right? That's why I said the general rule of thumb for probabilities close to 0.5, you have a little more leeway. And why do we want bell-shaped results? I told you we did. Why? This is a reminder. We want bell-shaped results so that we can use the empirical rule. The mean's in the center. We can go out one deviation left or right. I'll break this up into regions. Each direction from the mean is 34% if we go out one deviation, or 68% between these two. If I go out to two deviations, -2 and +2, each of these is 13.5%. And that gets us about 95% right here. It's close to 13.5. And so on and so forth. 3 deviations was 2.35, and past that was 0.15%. So if we have the bell shape, we know what the percentages are based on number of deviations from the mean. All right. Finally, 6.3 Poisson distribution. Pen is dead. I need another one. There's a new black pen. All right. So 6.3, the Poisson distribution requires a Poisson process. So we need the probability of 2 or more successes in a small enough interval is 0. For example, let's say we're counting the number of cars that come through the drive-through at McDonald's. if it's the number of cars and I say in a minute, I could get more than one car pulling up to the speaker in a minute. Definitely, if I did it in an hour or 15 minutes, there's a strong chance that the probability of 2 or more cars is greater than 1, or is not 0. So we want to get that interval small enough so that two cars in a small enough interval is 0. If I make it 1 second, there's no way 2 cars can pull up and go through the drive-through in 1 second. A small enough interval, I can make it 0. That's the premise there. The probability of success is the same for any 2 intervals of equal length. So if I say it's every 30 seconds and we can't get, it takes people more than 30 seconds to order. So the probability of having more than 1 car in 30 seconds is 0. But let's say the probability of having 1 car in a 30-second period is, there's not always people in line at McDonald's. So it has a value, and let's say it's fixed. And finally, the number of successes in any one interval is independent of other intervals. Assuming the intervals don't overlap. And in all reality, you're not going to want to have overlapping intervals. Let me give you an example. Do I still have it in my bookmark history? I don't need to show you all my bookmarks. That's bad. We're going to look at the food defect. Oh, there we go. I got it saved. Food defect levels. Fun fact, the FDA goes through and says how much you can have as a defect in a product before it becomes unsafe to sell to customers, including contaminants, damage to the container, extra materials, foreign materials like insects, rodents, birds, decomposed material, stuff like that, cigarette butts. And if you look at it, it bases it on what category you're looking at. So like I'll do a search for peanut butter. They have a requirement. It needs to be 30 or more insect fragments is a problem per 100 grams of peanut butter. 1 or more rodent hairs per 100 grams of peanut butter is a problem. Okay. Now, what about chocolate? Everybody, not everybody, most people like chocolate. Chocolate, 6 or more insect fragments per 100 grams. Rodent filth, shells from the cocoa bean, I would assume. So normally what I like to do is do this right after I hand out M&Ms and people eat the M&Ms, and then we go over the chocolate problem. Since we're not doing it live, I don't get to do it. Soon, when the pandemic is over, I get to go back to being a sick and twisted teacher. I find it hilarious. I enjoyed that part a lot. So our example that we're going to look at, the FDA, Food and Drug Administration, sets a food defect action level and they call it an FDAL for various substances that inevitably end up in our food and drinks. Inevitably end up in our food and drinks. Now, the chocolate one, where was it? Chocolate was 60 per 100 grams for chocolate. This is 60 insect fragments per 100 grams. And fragments include things like larvae, eggs, body parts, stuff like that. And if I convert that down to 60 fragments per 100 grams, if I do that division, 60 divided by 100, this is 0.6 fragments per 1 gram. All right. So what we're going to do, I'm going to pause it. I'm going to go grab a chocolate bar. This is essential for what I'm doing here. Let's make it real. All right, so I went and grabbed a Hershey's chocolate bar. There's 1.55 ounces in a Hershey's chocolate bar. It's 1.55 ounces. And how many grams is that? It actually tells us 43 grams, which equals 43 grams. All right. So let's look at the Poisson distribution for this. So if I get it down to a small enough interval, like grams, how much, like I get down to grams, it's less than 1. When I was doing 100 grams, that's a big interval. There's probably having more than 2 fragments is pretty large. But when we get it down to 1 gram, it's a small enough interval that it's less, probably having 2 is unlikely. I could make it even smaller, a half a gram, a tenth of a gram. Let's look at the probability of having exactly 3 insect parts in a Hershey bar. We can do fewer than 3. And let's look at least 3. What I didn't give you is the formula. And I'm going to give it to you now. So what's the formula? We'll put it on the next page. We're not going to use it, and you'll see why. If you go into something like calculus and stuff like that, you will use things like this. But if lambda represents, that's it's pronounced lambda, it's a Greek letter. Lambda represents the average number of occurrences or rate. Occurrences or the rate. And it's pronounced lambda. T is our interval, often time. And we're going to use X is the number of successes. The probability for a specific X, we're going to take lambda and multiply it by T, and we're going to raise it to the X power. Then we're going to divide that by X factorial. We've seen factorials before. E is actually a value. It's like 2.71 something. It shows up in nature a lot. We're going to raise E to the negative lambda times T. That's the formula. This is horrible by hand. It's really easy to screw up doing this in the calculator. Thankfully, we have Statcrunch. All we require for Statcrunch let's go look and find it. If you don't know, you can always look. What if I don't remember? Well, we're in the distribution section and we're doing calculators. So we're going to go stats calculators. And if you're not even sure if it's there, if you know it's a Poisson, just look through the drop-down menus until you see Poisson. Applets, we haven't done anything with applets really. Edit is editing the thing. Data is arranging data and stuff like that. We do a lot in stats and graphs. I don't see Poisson here, so I'll go to the first one down. Calculators, I see Poisson. Does it show up on summary stats? No. Does it show up on tables? No. Z stats, T stats, it shows up in one spot. Stats, so you might, if you don't remember, just look around for it. Look, don't be lazy, just look for it. I get a lot of people that are lazy, like, I don't know how to find it. I don't know where it is. Just look. Just look, okay? Go through the drop-down menus and see what you find. Most of the stuff we do is in stats or graphs. Stats, calculators, Poisson, what do we need? It wants the mean. It requires the mean. And what value of X we want. The mean for a Poisson distribution is lambda times T. Okay, so, and the standard deviation is the square root of the mean, or the square root of lambda times T. So let's go back to our chocolate problem. Pause that if you need it up longer. We'll go to the back of the chocolate problem. Back to the Hershey's bar and insect filth. There was 43 grams. The rate was 0.6 fragments per 1 gram. fragments per gram. That's my lambda. Lambda is 0.6. T is the number in the interval, or how much we're doing. T is our number of grams. So mu of x is 43 times 0.6. 25.8. And what kind of problems did we ask? I said probability that we have exactly 3 parts. Well, what I'm going to do is I'm going to go in and I'm going to enter my mean at 25.8, which means the average, if we have a 43-gram chocolate bar, the average number of insect parts is 25.8. So the likelihood of having exactly 3 my stupid bar is in the way. There we go. Is really low. 0.000. I think there's 7 zeros there. 2. Low. Fewer than 3 looks even lower. Fewer than is less than. (2.2441) e to the -9 is what my calculator says. This means 2.2441 times 10 to the -9, which really means move decimal left 9 times. If I move it left 9 times, I'm going to have 8 zeros over there. Really, really low. Probability of at least 3. At least 3 means I could have 3 or more than 3. One. Greater than or equal to 3 means we don't have 0, 1, or 2, which means we're subtracting that value right there, and that value is so small that it really doesn't affect the probability. We have 100% chance there's at least 3 insect fragments in that chocolate bar. What if I make it like 10? Oh God, look at that. Probability that x is greater than or equal to 10. 0.999866981, or 99.99% chance that there's 10 or more fragments. 20. 0.8965. Looks like the 6.5s keep repeating. If I move the decimal right twice, I got 89.656 or 66%. What if we put in the exact mean? Is it half? It's still over half at 25.8. So it's skewed right just a little bit. 30. Oh, changed the wrong thing. Well, now we're getting lower. Probability that x is greater than or equal to 30 fragments, or like a beehive, basically. No, that's a lot more than that. Now we're getting down. 22 is still high. So that's all we have for that. That is 6.3. That's how all these run. Most problems will tell you it follows a Poisson distribution. And having said what I said, I'll just leave you with a nice, pleasant image. Peace out. Chocolate's so good. Take care, everybody.